by introducing what sparse coding is and what Delaunay triangulations are. Okay. So let's assume that we have a set of vectors. Okay, so we have m vectors. These vectors live in some d-dimensional space. And our goal is to represent a data point y as a linear combination of these n vectors. Okay, so we can formulate this as a linear system because y is equal to a times x. And the goal in sparse coding is to have a representation where x is a sparse vector. Okay. So in this context, we refer to this matrix A as the dictionary, and we call X the sparse code. Okay. And there are many reasons why people do sparse coding, because sparse codings help you facilitate downstream computations. Okay. So sometimes this A can be predefined. So somebody tells you that, for example, you have to use the Fourier basis or the wavelet or the curvelet, or you can also learn A from adaptively from data. So the question is, if you just have this constraint, there is no reason to think that X will be sparse, right? We just do the least square problem. So one common approach to recover X is we employ sparsity regularization. For example, by doing L1 regularization, which promotes sparse solutions. So that's the first part. The first part is in sparse coding, we are interested in representing our data point as a sparse combination of a set of vectors that are either predefined or learned. Okay. So for the second part, I need to introduce the following notation. So let me introduce what a d-simplex is. So if we have a set of d+1 points in Rd, and if we take the convex hull, we call this the d-simplex. So let's consider a simple example. So a 0 simplex is just a point. A 1 simplex is just a line, and then, and so on and so on. So these points that make up the d-simplex, we call them the vertices of the simplex. Okay. So what do we mean by a face of the simplex? A face of the simplex is just a subset of a convex combination of the subset of s+1 vertices. Okay, so to make it concrete, if you have a 0 face, it corresponds to a point. 1 face corresponds to an edge, and 2 face corresponds to a triangle. Does that make sense? Doesn't make sense? Okay. Okay. So in this talk, I'll use the following definition of a triangulation. Imagine I have a set of points, and I have their convex hull. So the convex hull is the set of all convex combinations of the set of points. So we partition the convex hull into several parts, such that the intersection of any two simplices is either empty, so they don't intersect, or they share a common face. Maybe they share an edge, or in high dimensions, they share a face. So what makes, the one part I want to emphasize is there are multiple ways, as you can imagine. If I give you a set of points in R2, for example, there are multiple ways to triangulate, right? So the one triangulation that we are going to consider in this talk is called the Delaunay triangulation. And I'm going to introduce the formal definition and illustrate it with a picture. So what's the Delaunay triangulation? You pick up the set of m points, and it's a triangulation such that if you take a look at any of the d-simplex and look at a hypersphere that encloses it, the interior is empty. So this is easier to see with a picture. Okay, so let's take a look at this picture. So in this case, we are in R2, and I am partitioning my convex hull into different triangles. What does it mean to be a Delaunay triangulation? So let's consider this particular triangle here, and let's draw a circle that goes through these 3 vertices. Okay, as you can see, this circle does not contain any other vertex, the blue vertex, right? Any of the blue vertices. Okay. So if you draw a circle at any of the triangles that passes through these 3 points, it shouldn't contain any other blue points. Okay, so if it satisfies this property, we call it a Delaunay triangulation. For now, ignore the black points. The black points, I'll come back to what they are later on. Okay, so the next question is, when do you have a unique Delaunay triangulation, right? Because if I give you a set of points, it might be that there might be multiple Delaunay triangulations that we can do. So the condition is no d plus 2 points lie on the same sphere. One way to think about this is, imagine if you have a square and I can draw a circle that goes through the 4 vertices and I can triangulate in multiple ways. So in this talk, I'll always assume that there is a Delaunay triangulations, a unique Delaunay triangulation, and this condition is called the points are in general position. Okay, so when we say the points are in general position, it means that there is a unique Delaunay triangulation corresponding to this set of points. With high probability, this is true. Exactly, with high probability, this is true. So let's consider how we generate data. So it's a very simple model. We have this triangulation. So I give you these vertices, which are the blue corners, and each data point is simply generated as a convex combination of these blue points. Okay, so each data point in black is simply a convex combination of the blue vertices, right? So if that's the case, then we know that in this simple toy model, if I have a data point y, I can write it as a times x, where a is going to be the collection of these blue vertices, right? And x is going to be something on the simplex, meaning that it has to be non-negative and sum to 1, right? Because I'm taking convex combination. So each of these data points is generated as a convex combination. Now, however, even in this simple example, there are multiple ways to represent a data point as a convex combination, right? So for example, you can imagine if I'm on this triangle, I can represent this data point using these 3, or maybe I can connect this point here to this point, right? So there is multiple ways I can express this data point as a convex combination of these blue vertices. Okay. So we want to focus on a unique sparse solution. But before we even talk about unique sparse solution, we have to define what do we mean sparse in this setting? Like, what do we mean the sparse solution in this setting? Because, for example, if I have this point, I could potentially describe it as a convex combination of this point and this point. I could also use these 3 vertices, or maybe other set of vertices that enclose it.
Do you fix the sign of the coefficient?
The sign of the coefficient is fixed. Yeah. Okay.
Then that give you uniqueness.
Oh yeah. So the uniqueness, I'm going to define it in the following way. So let's focus actually on this point right here, right? If we focus on this point right here, it's natural to think that the most natural sparse representation will be using the vertices of the simplex that it belongs to, right? So among all the sparse representations, I want to pick the one for which it belongs to. So I want to just express it using this, this, and this. Okay. So we call that the sparsest representation, which is a representation based on the simplex I belong to. So in R2, it's a triangle. In higher dimensions, these are going to be these simplexes. Now the question is, how can we do this? Can we design an optimization algorithm such that when we minimize it, it will actually give us, among all the representations, it's going to pick the one where to the triangle that I belong to. Is the problem clear for everyone? Okay, so the goal is I have a triangle, I have a bunch of triangles, I have a point in one of the triangles, and my goal is, among all the ways I can write y is equal to a times x using the vertices, I want to pick the one which is using only the triangles I belong to. I assume that I know this DTA. Yes. For now. Yeah, I already partitioned that. Yeah. So now for the first part of the talk, I assume I know DTA. Yeah.
You saw them pick up the sign.
Yes. So here is the trick. So let's say that we have the DTA. So I'm going to spend a little bit time on this since the technical definition might be confusing. So whenever we have a Delaunay triangulation, we have a center associated to it. So each triangle has a center, and that center is equidistant from each of the vertices. Okay, so the center of each triangle. So in R2, it's a triangle. In higher D, that's going to be the D simplex. Okay? So imagine that you're given the Delaunay triangulation with some center C. Okay, so Z, this particular point Z belongs to one of the triangles. Now we define the following weighted L0 norm. So what do I mean by this? So let's forget this scaling factor for now. So this is counting the sum of the distances from the centers to each of the vertices that you use to represent yourself. This is what this indicator function is doing. Okay, so just to go back to this picture, for example, if I use this point, if I represent this point using this point and this point, then that indicator vector is going to be 0 everywhere except at these two positions. And my weighted L0 norm is going to be the distance from the center of this triangle to this one, and the distance from the center of this triangle to this one. Okay, so average distance. So, and it's normalized by the weighted L0 norm. So any questions? I just want to pause here and.
But C is just choose one. This not definition depends on the choice of C.
This definition depends on the choice of C. Yeah. So I choose the center. I choose the center of the triangle, and then I'm looking at the distances from the center of the triangle to each eye, but only the eyes which I'm using to express my data points. So the ones I'm not using, I'm not considering them. Okay. Now, so let me show why this will help us recover the sparse solution. So this is an intermediate lemma. If you have a D simplex of a Delaunay triangulation, so in R2 that will be a triangle, then there is always a hypersphere, and this follows from the Delaunay triangulation definition. There is always a hypersphere with center C and radius R, such that from the center to each of the vertices, the radius is R. That's by construction. And if it's anything outside, it's greater than R. Now, the proof of this lemma is exactly the definition of the Delaunay triangulation. Because if this was not greater than R, then that means that you have another vertex inside that circle, which will contradict the earlier definition of the Delaunay triangulation. Okay. So using this lemma, we can actually prove the following. If we minimize this L0 norm, subject to this constraint, and we all agree that there is multiple ways to express my data point as a convex combination, then this solution actually recovers this, the sparse solution where the sparsity is concentrated on the triangles you belong to. Okay. So among all the solutions you can represent yourself, it's gonna choose a solution where it's gonna be the triangle or the simplex you belong to. But one thing that's not nice about this is, as we can see, it depends on C, right? Which, for example, if you do Delaunay triangulations in high dimensions, you have to know the C for each of the triangulations, right? Okay. Now, yeah.
But is that true? That's might be true. So if you see the X, right? If your X sitting in that triangle,
yes,
the barycentral coordinate has to be positive. That gives you uniqueness.
Yes.
So in other words, if you take a look at coefficients, if the coefficient summation is equal to 1 and everything is positive, then you may have the unique solution. Or if you ask the sparsity as a D plus 1, then that has to be unique.
Yes.
Which means there might be the other way to regularize. I'm not sure if it's easy.
Oh yeah. So exactly. So the next part is actually how do you regularize this better? Exactly. So the one thing that's not appealing to this one is this very complicated indicator function, right? Which is not nice. So the goal is, can we replace it by something nicer, right? So the idea is maybe we should actually use the x's to regularize, right? Because we know these coefficients. So we should actually use them to regularize rather than just using the indicator function. Yeah.
So your assumption, you assume every point belongs to one simplex, or it can belong multiple simplex?
Just to one simplex.
Just
One
because
simplex.
your condition is
That's actually why, like, I assume the uniqueness of the Delaunay triangulation, so that
intersection of this triangle.
the intersection is either like a face or empty. Yeah,
It's a simplicial structure.
it's a simple shell structure. Yeah.
But even like in one simplex, right? But if I pick another 3 vertices, right, it could be give you a larger simplex, but that simplex may not be your partition, right?
Yeah. So this one is going to find the minimum one that you belong to.
I mean,
So, yeah.
For example, here, right?
Yeah.
You have that, let's say that the right one.
Yeah.
That you have 2 points.
Yes, this one.
Yeah, let's say the lower points.
Yes.
Of course, in that triangle, right? But you can pick another 3 vertices. That point can still be a convex combination of that 3 points, right?
You mean this one, and this one?
Yeah, maybe, right?
Yeah.
But that 3 points, the simplex formed by that 3 points, not in your triangulation, right?
Yes. Oh yeah. So what this is saying is actually, even if you consider this, for example, for this one,
yes,
if you solve the weighted L0 problem, it's not going to pick this, and this. Even if that's a valid solution, it's only going to pick this, and this.
Why? Because you're C?
That's because of that's essentially because of this definition. That you see, this is being weighted by.
Oh, I see. You want the smallest one.
Yes,
okay.
yes. So there could always be a bigger one that contains it, but I want the smallest simplex that contains it. So one nice thing about triangles is that if you do the convex combinations, for example, let's just focus on this picture here. If I do the convex combination for this point using this, and this, the weight is going to be larger on this one compared to this one, for example. So naturally, the weights in a convex combination actually inform you about distance. If you are very far from a point, the weights are actually going to be small. Okay? So now we're going to use that for our purpose to actually come up with a different regularization, which is nicer. So what does this regularization do? Compared to the previous one, it's exactly the same. The only difference is now I'm weighting the distance to each of these vertices by xi, where xi is the weight on the i's data point. Does that make sense? So I no longer have this indicator vector. I have this regularization where xi is playing the role of the indicator vector. Now, if you look at this, since we are in the setting of convex combinations, xi's are non-negative and sum to 1. So if I ignore this term, this almost looks like an L1 norm, right? So if I ignore this one, since these terms are positive, this is like an L1 norm. So we can interpret this as a weighted L1 norm, where the weights are coming from how far your data point is from the AI. As you can see here, I've also removed the C completely. I've removed the C, and I'm saying for each data point, I'm just going to look at how far I am from the other data points and weight by these weights, and that's going to be my weighted L1 norm. Okay. So surprisingly, the question we're going to answer is this weighted L1 norm also going to work? Because the previous one was in some sense a little bit of cheating, because we assume we know the center, we assume we have this indicator vector, but this one is a more nice optimization problem. So we consider this optimization problem. Once again, we have many ways to express our data points as a convex combination. And the question is, does this recover a sparse solution? And what kind of a sparse solution does it recover? So one result we have is that the solution for this is actually exactly concentrated on the D simplex of the Delaunay triangulation that your point belongs to. So in other words, if you have a Delaunay triangulation, and if you have a point, and you want to find your convex combination that only uses that particular simplex, then you can solve this optimization problem. And the optimal solution for this optimization problem is only going to be concentrated on the vertices of the simplex that you belong to. Yeah.
It looks like your program, that weighted L1 program, is independent to your DTA, right?
The DTA comes, that's quite right. Yeah, that's quite right. So the DTA shows up, we did the DTA for the proof. So the DT is like a regularity. We cannot have like you remember one of the defining properties of the Delaunay triangulation was that if you draw a circle, you cannot have another point. So where that assumption is coming is.
But does that mean if I give it this endpoints, you can only have a unique DDA?
If they are in the general position, yes. And
always
almost always, if you have a set of points, almost always there is a unique Delaunay triangulation.
You already have unique.
Yeah.
Otherwise,
you're right. If I don't have uniqueness, there might be multiple. Yeah, there might be.
But there could be another way to say, right now you ask X, the summation is equal, M of them summation is equal to 1. You can ask D of them, D plus 1 of them. Because in a triangle, now there is
that's true,
the union of those things. And you basically you penalize the L0 norm, because the L0 norm is equal to D plus 1.
That's true.
You ask for positivity and also give you uniqueness.
Yeah.
But of course, the beauty of this kind maybe is easy to solve.
Easy to solve, yeah. Easy to solve, yeah. So the next question is quite easy. So let's say that we have this point and we move it around in this triangle. So the question is, how does the X change? Right? So this is essentially a stability problem. We move the point around in this triangle. What happens to the X? Right? It's a stability problem. I'll give 2 results, and one of them is just a linear algebra result, but the next one is actually quite interesting. So the first one says, okay, if you solve the new problem where now you have some noise, then the true solution compared to your new solution, any solution that you get for this problem, it's going to be bounded above by the noise, which makes sense, right? So the more noise you have, the 2 solutions, the solution for the perturbed problem and the exact solution to the original problem will be very different. And another thing is this minimum singular value of this matrix, which essentially captures all the geometry of the Delaunay triangulation. And one intuition I would like to give you is that this minimum singular value essentially tells you if your triangulations are like very skinny or very fat. And very skinny triangles are actually quite hard for the stability. So essentially we have a stability result that depends on how much noise you have. Of course, the larger the noise is, the more the difference between these two. The upper bound is going to grow. And the second quantity is, it depends on some geometrical characteristics, which is captured by this minimum singular value. So I claim that we can actually do better than this. And this is based on the following very nice characterization of simplex coordinates. So let's do this in R2. So we have these 3 vertices. Let's say this point is expressed as C1A1, C2A2 plus C3A3. Okay, so we're expressing this point as a convex combination of these 3 points. Actually, we can actually express CI in a geometrical way. So C1 corresponding to the weight we put in A1 is the ratio of this area right here divided by the whole area of this triangle. So C1 is the ratio formed here, right here, divided by the whole area. C2 is this area right here by PA1A3 divided by the whole area of this, and so on and so on. Does that make sense? So to find CI, we remove that vertex and we look at the area formed by the remaining ones and divided by the whole area. Now, what's nice about this? So as you can see, if P is very close to A1, then by this argument, we know that this CI is also going to be quite large, right? Because most of the area is going to be coming from this part. Does that make sense for everyone? So the message is that the simplex coordinates can actually be expressed as a ratio of areas. And this generalization carries in these simplices, it becomes ratio of volumes. Now, why does that help us? Now, the question of stability becomes the question of how much is the area or volume changing as I am moving around the triangle, right? Because as I am moving in this triangle, all I have to do to compute my coefficients is compute the ratio of these areas, right? And the question of stability is a question of how much does this area or volume change. So fortunately, we have a very nice formula. So this is called the Cayley-Menger determinant, which if I give you a set of d+1 points, then it helps you essentially find the volume by computing this determinant. The most important information is this d. So this d is the pairwise distance between this A0 to AD. Okay, so if you have a set of points, you form the pairwise distance matrix. You have a one vector, sorry, this should be a 0 right here. And you find the determinant and you have the volume. Okay. Now, one can show that, I'm going to skip the details since it's a little bit technical, but one can show that then now that we have stability where the stability depends on this determinant. And as you can see, this determinant only depends on the distances, right? So if we know how much the distances are changing, we basically have an estimate on this determinant. Now, before I go to the next part, I just want to emphasize that all of this stability and uniqueness results depend purely on geometric conditions, right? So this is quite in sharp contrast to compressive sensing conditions, which require very strong conditions on the dictionary, right? So this is purely conditions, local geometric conditions of the triangulation. So these are very structured triangulations. And if you apply the standard sparse recovery results, they don't hold in this setting because they are highly correlated dictionaries. Okay, so these are highly correlated.
Because the conventional way is every point talk to each other. This
Yes.
one just has local.
Yes, exactly. Yeah. So here everything is local. Exactly. Yeah. Yeah. So here, like, we basically don't have any global dependence. That's why the stability and everything is going to become for free. So far I have sort of done a toy model where I said, okay, if I give you this Delaunay triangulation, we can have this nice weighted L1 norm that helps me recover a sparse solution. But the question is, of course, in practice, we are given data and we don't know what's a good triangulation of the data, right? So we actually have to learn these triangulations. The triangulations are not given to us ahead of time. So the first part of the problem was, okay, say somebody gives you a triangulation which generates your data. Then you can do this procedure.
But in your optimization problem, you don't need the triangulation. In your theory, your proof you need, right?
In the optimization problem, you don't need the triangulation.
Right, but then what? Then you don't have to have the simplicial structure.
Yeah, so exactly. So we completely dropped the simplicial structure here. Yeah, exactly. Yeah, so the only part we need the triangulation is for the proof. So let's take a look at this regularization, which we have seen before. So now imagine that I give you a lot of data points, yi, right? So we have y1, y2, up to yn. Then we can consider minimizing this regularization over all our data points, okay? Now let's see what this does, which we have looked at earlier. Okay? So why does this regularization promote sparsity? Now, yi minus aj, when this is very, very large, what does it mean? It means that your data point yi is very, very far from aj, right? That means that you want to put a smaller weight on this one. Okay? And if this is small, if yi and aj are close, then you have a freedom to put more weight on here, right? So this is encouraging sparsity but a specific type of sparsity by only trying to promote sparsity on things that are closer to you. Okay. So you can interpret this in many ways. I'll just quickly show some of the interpretations. For example, you can rewrite this as a certain graph matching problem, one-sided graph matching problem, where you can think of this to be the cost matrix. So imagine that you have your data points on one side, and you have these vertices, the A's on the other side. And what's the cost? The cost is the distance between them. And you are trying to find a matching between them. So you can think of the Xij as being able to match your data points to the vertices. Okay. So similarly, I'll not go into the details, but you can also think of this as some, you can actually give an optimal transport interpretation of this problem by defining empirical measures. Okay. Now, let's consider a simple instance of this where Cij is a binary matrix, right? If Cij is a binary matrix, then this essentially becomes the the k-means problem. The k-means problem. Now, here is the unfortunate thing about if you just consider this regularization problem without putting the y is equal to a times x constraint. So if I ignore the y is equal to ax constraint, this is basically, in some sense, just becomes like a k-means problem, you know. So it just becomes like a binary assignment matrix. So what makes this problem interesting is not just this regularization on its own, but the fact that we are also required to reconstruct our data points. So the y is equal to ax constraints.
So you are simultaneously looking for dictionary and also the coefficients.
Yes.
Without regularize the coefficients. Or regularization of the coefficient is just summation is equal to 1 positive?
Yeah, I agree. Yeah. That's all the thing is. Yeah. So that's what I'm saying. This problem is in some sense not interesting because we don't really have like a fidelity term, right? That tells us how the in some sense ill-posed, yeah. So let me give a graph interpretation of what's happening. So the blue points, think of your data points, and the red point are these A's that I've been talking to, which is the atoms. So we call them the atoms or the dictionaries. And the weight of this graph is exactly the x's, right? So if this data point is using some weight to represent itself using this particular atom, that will be this xij. Okay. So in other words, we have automatically a graphical interpretation. We have data points and atoms, where the atoms are these vertices, and they are connected by the x's, the xij. So you might say, why do we care about this? Well, now we can, if we have a graph, we can actually define an adjacency matrix, right? And we can define the graph Laplacian. Okay. And if you basically compute this and do some algebra, you see that this is what people sometimes call Laplacian smoothness. Okay. So you can show that this is actually a certain smoothness in the graph sense. Okay. So what's our model? Our model is the following. The goal is to learn this what we call this the red points that I've shown you earlier. So this A1 to AM, we call them the landmarks or the dictionary. So we want to learn this. For now, let's just assume the case that everything can be represented exactly. So we want to do y is equal to a times x. Our coefficients are restricted to be non-negative and sum up to 1. So each data point is a sparse convex combination of other points, but these points in our new framework are also going to be learned. So we don't know them. So in the first part of the talk, I already gave the triangulation and the set of points, but now we don't know them. So we are going to learn them as part of our optimization problem. Okay. So let's just focus on the A problem. Actually, the A problem is easier. So we have to learn both A and X, but let's just ignore the X for now. Then if you do this, actually, you can show that this actually has a unique solution. So you can actually prove that this problem has a unique solution. Okay. And you can actually write the closed form solution in this way. Okay. But if you want to optimize over both A and X, that's going to be slightly different. So I'll discuss the algorithm in the next section. So the question now is, how can I use this to, so say that I have a set of data points. Somewhat, I learned some good A and good X, right? How can I use this to embed my data, right? Say my data is in high dimensions. How can I use this procedure to be able to embed my data in low dimensions? Right? So we solve a very standard problem. This is coming from a spectral problem. If you remember, this L is the same Laplacian that I showed earlier. Okay. And under some assumptions, we can show that the spectral problem reduces to a spectral problem in the A. So let me try to emphasize what this means. So what this means is that typically when you do a spectral embedding problem, the spectral embedding problem is done for all the data points, right? So your Laplacian is going to scale with the number of data points. In this procedure, your Laplacian will only depend on the number of the landmarks A, which is going to be significantly much smaller than the number of data points in typical problems that I'm going to show later on. Okay, so we can show that the spectral problem over the data points is equivalent to the spectral problem over the atoms. Okay. So let me skip this in the interest of time and directly go to the algorithm. So this is the algorithm. This is the problem that we want to solve. This is the optimization problem. So we have a bunch of data points. We want to learn this A. So these are the red vertices that I showed you earlier, right? So these are the dictionary. I also want to learn simultaneously all the xi, which I put on this big matrix X. And I require that all the xi's are non-negative and sum up to 1. So they lie in the probability simplex. So how do you solve this problem where we are optimizing over both A and over both X? A standard approach is to do alternating minimization, where you fix one of the variables and optimize over the other, and then you alternate between these two steps. So let's focus on the first problem. So the first problem, I fix A, I assume that I know A, and I consider the optimization over the X. Okay. So this is a nice problem. This is a weighted, right? This is a weighted L1 norm in this case. And so this problem is, has nice structure. So we, this is called a convex problem. And this is also convex set because this set is just the probability simplex, right? So everything has to sum up to 1 and is greater than or equal to 0. So we can do an accelerated version of the projected gradient descent. So don't worry about the details of the algorithm. What this does is it basically takes a gradient step and projects it onto this set. So I'd like to focus on this set for a little bit. It turns out that we can actually project exactly onto this set. So there is a closed form solution that if you have any point, there is a closed form solution to project you onto the probability simplex. Okay. Then we can do the multiple iterations of this to recover the optimal solution X. Okay, so if A is fixed, this is a standard and well-known problem where we can just call an accelerator projected gradient solver and run it. The only thing you have to do is the projection. This is the only thing. The only thing you have to do is you have to define this projection here. One could also solve this, maybe not using gradient descent, but something like Fraunhofer, because this is a convex problem over a convex set. And if you do that, here, this part of the problem has actually a closed form solution. So this is another approach. So my point is that for this part of the problem, there are already existing standard optimization algorithms to solve it. Now, how about if we fix X and optimize over A? Okay. So for this problem, we can also do gradient descent. Okay. So what does the algorithm look like? You start with some initialization. You optimize over your X. Then you optimize over A, optimize over X, optimize over A. So you alternate between these two steps. So this first step, where you fix A and optimize over X, is called the sparse coding. And the second part, where you fix X and optimize for A, is called the dictionary learning. Now the question is, can we sort of design an efficient, can we recast this as a neural network? So can we map these two optimization problems into a neural network?
Before you go there, so this factorization AX, if you change both A and X, do you have ambiguity? Right now you fix the sign of X, because you don't, conventional dictionary learning, the dictionary is like orthogonal, for instance.
Yeah.
But now you don't need that.
I don't need that, yeah.
So do you have a possible rescaling? So you may not have a rescaling ambiguity, because X is fixed from between 0 and 1. Sign also.
Yeah, so yeah, the X being on the simplex, yeah, does help in that regard. So I'm going to briefly introduce what algorithm unrolling is. So algorithm unrolling is, say that you have an optimization algorithm for your problem, and you want to map it to a neural network, right? So you want to map it to a deep learning problem. So this is called algorithm unrolling because you take an algorithm and you realize it as a neural network. So you can map any algorithm you have as a neural network architecture. Okay. So there is a lot of work on this. So in our case, we use a particular architecture called autoencoders. So this picture looks complicated, but I'm just going to show what this does. So remember that our first step is sparse coding, right? So I give you a data point, and the goal is to compute the sparse code. Once I give you the sparse code, the next part is doing the dictionary learning, right? So let's see this in this picture. So all of this, what you see here is doing is the sparse coding. And this repeat t times is just doing t iterations of the accelerated projector gradient descent. Okay, so this is the encoder part of your architecture. And what it's doing is accelerated projector gradient descent multiple times. Now, what's the activation function? The activation function is going to be exactly the projection onto the probability simplex, which actually can be realized as some modified ReLU function. Now, once you have the code, which means that x vector, how do you approximate your data? Well, if you have some x, the way to approximate your data is just a times x, right? Approximately. So you can multiply it by a. But of course, as we said, we don't know a. So what does this a become in the neural network? This actually becomes the weight of the encoder. So there is a linear layer that takes your data, just multiplies it by the A matrix and gives you the output. Okay, so the autoencoder architecture, for those who are not familiar, has two parts. The encoder part takes your data from high dimensions to some low dimensional representation, hopefully. And then the decoder part, which takes the middle part and gives you some output, which is similar to your input. So we have an input data, here. So we have an input data Y, an output data Y, and our goal is to minimize the input and output to the extent possible. Okay. So
this is also different from conventional autoencoder. Your A and A, they're the same or they're not the same? You encoding and decoding procedure.
Oh yeah, so they are the same. The only difference is that when I learn my A here, I'm going to back propagate through the whole network, not just through the decoder.
I see. Because the encoding, decoding, conventional.
That's right. And what this does, we haven't shown it in the context of this particular problem, but people have shown that doing the back propagation through this whole network as opposed to the decoder gives you some accelerated convergence guarantees, but we haven't shown this in this particular problem. Okay. So just to summarize, what's the algorithm? You give me some step size, you give me your data points and some initialization, you do the sparse encoding in the encoder, then you just multiply by this matrix A to get the output, and then you do back propagation to learn your A matrix. Okay. So let me show some results. So I wanted to sort of provide very intuitive cases where we can actually think of what the dictionary should look like, right? So this is just two circle data, and then this is the moon data. And these red points are what the algorithm learned to be the dictionaries, which makes sense, right? Because anything, for example, in here can be approximately written as a convex combination of its nearby neighbors, right? Its nearby neighbors. And similarly here, it learned to put these red points, which are my dictionaries, so I can approximate any point as a convex combination of my nearby points. Now, yes. You have to pick the number of atoms. I'll come to that question. Very, very, very good question. Yeah. So unfortunately, one of the challenging problem in this is how do you pick the number of atoms, right? How do you pick the number of atoms? So that's a problem that we are studying. And let me show you by an example. So I consider the two circle problem, and I actually do clustering based on their sparse cores. Okay, so if I can tell the two circles apart perfectly using my atoms, I call that 100% accuracy, which is the case here. As you can see, as the number of atoms increases, I get better accuracy, right? But the harder problem is as a function of dimension and the number of data points, how many optimal number of atoms that do you need? So to understand that a little bit, I did this experiment, which is, let's take these two circles and move them closer to each other. So as you can imagine, as they move closer to each other, it's going to become harder and harder, right, to be able to separate them. So we will need more dictionaries. So this region is, as the separation increases, after some separation, you always get this nice region, which is everything is nice, right? So if the two circles are separated, it doesn't even matter what the dictionary size is, right? So around here, we always get, so this region means the accuracy is 1. And what's happening here? What's happening here is that when the separation between the two circles is very small, or the dictionary size is very small, then we get failure. So what's interesting between these two regions? The interesting is what's exactly the phase transition, right? What's the phase transition between these two, which will basically help us quantify how many atoms we need as a function of some intrinsic geometrical quantities. But this is something that's still ongoing.
Can you explain a little bit on this? Is it the separation of two circles?
Yeah.
Is still one equals another one, or?
Okay, so one circle, yeah, out, and then another circle that contains the same circle. So two concentric circles.
Yes, you have a big one.
A small one, and then what the only thing I change is I bring one of the outer circle, closer to the inner circle. The distance between the
right.
circles.
Why? Get the intuition. Why you come closer, become harder?
Yeah. Let me give that intuition. So why it becomes harder is that you see.
First of all, how you measure accuracy?
Yeah. So good question. So how do I measure accuracy here? So for each data point in the circle, I have a sparse representation. And then I just take that sparse representation and pass it through a spectral clustering algorithm. So now, as you can imagine, when the two circles become closer together, you are going to be using not only atoms from the circle that you belong to, but from the other one. Because our regularization does not necessarily know whether it belongs to that circle or to the other one.
So when they overlap, but do these atoms also the same, or? Yeah,
so these atoms, unfortunately, as you can see, like.
So you mean you do the test that you first choose the atoms?
Yeah, you choose a set of.
Like
So essentially, like as you can see here, like when the separation is really, really small, you really have to push the dictionary size so that hopefully your sparse representations are not misleading, right? Because if you don't have a lot of dictionaries, what's going to happen is that a point in the inner circle is going to use the dictionary atoms from the outer circle to represent itself. And then that sparse representation basically is confused, so the spectral clustering just doesn't work.
Okay.
Yeah, you have to use only atoms from.
That means you cannot differentiate it.
Yes, exactly.
You can do some sandwich reports the same.
Yes, yeah. So in this one, what I was interested was to see like how does the phase transition work if you just use like a very baseline spectral clustering, and then. But I agree with you. There's more ways to separate these two. So this is just to show like how the optimization algorithm evolves. So as you can see, initially these points are kind of put randomly, and then they move around, and then they, after some training, they converge to this solution. Okay. So just to see like the sparsity, I did this experiment where, say, we take 5 digits of MNIST. So we take the digits 0, 3, 4, 6, and 7. So that will be about 35,000 digits. And I chose, for this problem, 500 atoms. So I have 500 atoms and 35,000 data points. And the question is, on average, how many atoms is a given data point using? On average, right? And as you can see on this histogram, on average, a data point is using 2 to 6 atoms from the 500 atoms. Now, it's not all data points are using the same 2 to 6, right? So as you can imagine, you have this MNIST data which lives in high dimensional space. We have sort of found optimal triangulations, and we're basically using only the local combinations to represent ourselves. And the thing is, okay, so now if we learn this is sparse coefficients, what does that, can that be used to distinguish between the digits, right? Because this is a compressed representation of our data. And the answer is yes. So if you do, for example, here I actually did all of the 10, and I have 1,000 atoms. And as you can see, if you do like, this is a TSNE visualization, some low-dimensional visualization. As you can see, this plot was done by using the similarity of the sparse coefficients, not the data. Okay, so if you try to do this by using the similarity of the data points, you get things that are kind of mixing together. But what this picture is telling you is that the sparse coefficients essentially allow you to tell apart the different digits, because all the digits cluster in their own group. So we compare this to a couple of clustering algorithms as well as manifold learning algorithms on the moon data, the MNIST data, and the YEL data, FS data set, and hyperspectral data set. The only reason we chose this MNIST 5, the 5 digits of it, is that because some of these problems are very poor. For example, the second method, it basically doesn't do anything beyond 30,000 or 40,000, so we cannot run the full MNIST on this one. Okay. And here is the clustering accuracy across all the different data sets and across all the different methods. And one appealing part of this is that we get these A's, which are something that you can post-process, or most of these don't have a dictionary attached to them. So we have these dictionaries that you can use for subsequent tasks, which I'll describe. Okay, so let me describe some of the ongoing works, which is, for example, how do you say that you did this procedure? Yes. Yeah.
So the numbers here, did the same, measured in the same way as in the circle?
Yeah, exactly. I run spectral clustering on the sparse coefficients.
It's like how easy is this embedding for
clustering? General clustering problem. Yeah, exactly. So for example, in MS5, you run the algorithm, you get the sparse codes, you pass it through a spectral clustering algorithm, and how good is the sparse code produced by this method? So this is some recent work that's still ongoing. So imagine that you have this digit 1 and you have this digit 0, right? And our goal is to walk from the digit 1 to digit 0, right? So I have digit 1 and digit 0, and I want to smoothly go between 1 and 0, right? Now you could do that in many ways, but here is one way, right? So say that we learn our dictionaries, right? So we have already learned the AIs. Then I could basically find the closest atom to my first data point, and I could find the closest atom, and I could walk across the edges of this graph. Okay. And I'll be happy to talk more about this. But essentially, since we have a graph structure going between two data points, right? Because what are the weights of our graph? The weights of our graphs are these positive xij's. So we can actually talk about shortest paths on this graph. And this middle picture you see is the one. If I do this setup, how does the one go to 0? So what I provided to the algorithm is the first one and this one. So as you can see, it's working very slowly. It's slightly transitioning to this, something that looks like an 8, and then finally going to 0. Yeah, unfortunately, one of the challenge for this is we don't take into account like rotations and stuff in our model, so that's why some of these things are kind of flipped. So I'll not say much about this, but one might ask, all of this work so far assumes the Euclidean distances. I'm just assuming that the natural distance between two data points should be Euclidean, right? One could ask, what happens if you change the distances for this problem? And one approach is to do, this is common in optimal transport, which is called a barycentric reconstruction, is imagine that your data are probability distributions, then the natural distance is the Wasserstein distance, and you can actually apply this procedure in this setting. But unfortunately, it's very hard to prove things in this case. So we have an algorithm, but we don't know how to prove anything in this setting because that barycentric reconstruction is highly nonlinear. So currently we are exploring the interpolation, like maybe using this for interpolation in high dimensions, further stability analysis, and imagine that the data is not given to you at once, but maybe streaming data. How do you apply this procedure? And one thing we haven't done is we haven't carried out any convergence analysis for the alternating optimization. So there is a student working on that convergence currently. Yeah, and this is acknowledgement, and yeah, thank you.
Any questions?
Like the early slide when you're talking about sensor. The one after regularization. So so if you just have one triangle, the center could be outside of the triangle.
That's right.
So does this also work for that case?
Yes, it does work for that case. Yeah, that's a good question. So one thing that affects also the analysis in the weighted L1 case is essentially how acute or how obtuse the triangles are. And I think in finite elements, for example, people understand this quite well, which is that whenever you have what's a bad mesh? A bad mesh is like where you have very skinny triangles. And the same type of conditions actually comes up in our analysis. So that minimum singular value is how nice are your triangulations.
More question?
So, can you go back to your histogram?
Yes, yeah.
Oh, sorry, the histogram.
Oh, yeah, sorry, yeah. This one. Yeah.
So I was just wondering, is that reflecting some sort of theoretic information about the word triangularization? Unusual that we have different numbers.
Yeah, very good question. So I think what this is telling in some sense is that even if these MNIST digits are in this case each digit in 784 dimensional space,